Let's take a look at the delta functions, the on-shell delta functions, since those are, in some sense, one of the keys here. So we started out with delta functions that had the form p1.q plus q squared. Now, of course, with delta functions, you can scale h bars in and out, but imagine for a second that this isn't exactly a delta function, but it's some element of a delta convergent sequence. So what's going to happen if we didn't switch to the wave number variables is that we essentially have an h bar inside this delta function. So we're going to get a delta of 0. Now, of course, if you could do the integrals exactly, it doesn't really matter what variables you do them in. But it's telling you that you're ultimately getting a kind of 0 over 0 problem. And the way you resolve that is precisely to do what I snuck in earlier, namely to shift to the q bar variables from the q variables. And in terms of those, then the simplest form is you get q bar dot u after I've scaled out the, and so the q bar variables are the natural variables. And that's telling us that for certain of the momenta, we should actually think in terms of wave numbers rather than momenta. And we'll see in a couple minutes how that affects the scaling. Remember that if we just included the h bars that are coming from the couplings, we seem to have a singular behavior. Now we're going to be, you can imagine we're changing, for example, from d4q to d4q bar. That's going to produce an h bar to the fourth. So now we're going to get some compensating factors of h bar, and we'll see in a few minutes how that all sorts itself out. There are just a couple of quick caveats that I want to mention. So remember, there was the h bar squared after we changed variables. We had something like q bar dot u, u1, for example, plus h bar q bar squared over 2 m. And you might wonder, why don't I just throw away that, that second h bar term? So the caveat is that in general, once you go beyond leading order, there can be individual contributions that are actually singular in h bar. So then, and it's only when you form a physical observable that those singularities cancel. But of course, in the intermediate stages, just as when you're doing dimensional regularization, you need to keep track of all the factors of h bar. That would be the analog of keeping all the factors of epsilon until you've actually done the pole cancellations. And what's going to happen is that when you take that into account, you're going to get derivatives of delta functions in general. So that's a feature that you'll see emerging in some of the results, not results we'll see explicitly today, but some of the results, for example, in the paper, they have derivatives of delta functions, and that's really the origin of those. Now, one thing I won't have time to discuss in detail, but it's related to this point, is that you might wonder, why don't we just set c equals 0? Why do we have to go through this complicated limiting procedure? And one of the reasons is the fact that in the intermediate stages, at least as far as we know how to phrase the calculations today, they're cancellations of singular terms, for example, between the I1 and the I2. The other has to do with the fact that there's a mixing or some potential confusion between classical orders and quantum orders. And we have to be very careful not to set classical parameters like the classical radius. We have to not set that to 0. And that's generally easier to do if you expand in C rather than setting it to 0 ab initio. Now, Q is not the only momentum in the problem. We also have these momentum transfers that we saw. And in general, when we're doing loop calculations, there'll be loop momenta as well. You can go through very similar arguments for the momentum transfers as I went through for this momentum mismatch Q. And you'll find that for the messengers, that if these momentum transfers correspond to photons or gravitons, again, you need to express things in terms of the wave numbers in order to have the natural variables. And likewise, for the loop momenta that correspond to the photons or gravitons, again, you have to look at the wave numbers rather than the momenta. And those will provide additional sets of additional factors of H bar that will ultimately give us a smooth classical limit. So it's convenient to introduce a little bit of notation, these double angle brackets, and what will mean we have some function of the incoming momenta, and that's going to talk about taking the leading term in the xi goes to 0 limit of our phase space integral with all the wave function factors and with all the messenger momenta replaced by wave numbers and appropriate factors of H bar taken out. And in addition, as I alluded to, with the momenta, remaining values of the momenta set to be their classical values, which are simply the masses times the classical four velocities. So what that would give us, for example, if we look at the very lowest order contribution, the classical limit for the first term. So the I1, again, because it starts at the tree level of linear and amplitude, it's going to be of order g squared, whereas I2 is quadratic. So even if you just put in the tree level amplitudes and you have no additional radiation, it's going to be order g to the fourth. So this is already next to leading order contribution, and there'll be an interplay between that and one loop corrections to I1. But in the next few minutes, we'll just have time to look at I1. So if we think about taking the classical limit, then we have, using this double angle bracket notation, we have the core left over. We have these integrals, and here you'll just have to take my word, but of course you can go back and verify that here, in fact, we don't need to worry about any singular terms, so we really can drop the h bar, q bar squared terms inside the delta functions. And as I've said before, the theta functions don't really play any role, so let me just drop them. And we now have q bar, so we had q over h bar, we now have a q bar. And let me actually still write that here. And we have our amplitude minus q. So we now can finish off removing the factors, changing variables from q to q bar. So there's going to be 4 factors of h bar from the measure, but there's going to be 2 factors in the denominator when we rescale the delta functions. And finally, there's another factor of h bar from the explicit value of the momentum that we're measuring. So let me quickly change variables here, q bar, Q bar, Q bar, and the net of H bar cubed. Now, I still, of course, have the factors of H bar in the coupling. Let me denote the amplitude with the coupling removed, or set to 1, however you want to phrase it, again by a bar. And we're just going to be looking at the tree amplitude. So that is going to, see if I can manage this here. Oops. That'll leave us with H bar squared. And there's a factor of the coupling squared. And there's also a factor of 4 from the delta functions, which I forgot to write out. So we now have a factor of H bar squared in front. And we're still not quite done with the factors of H bar, because we need to actually look at the amplitude. And the simplest amplitude is the lowest order contribution, of course, is something that's represented by just a single Feynman diagram. So imagine that we have we're thinking without spin here. So we just have two scalars scattering, and they're exchanging either a photon or a graviton, depending on whether we're thinking about electromagnetism or gravity. So we have P1, and again, from the scattering amplitude point of view, the primed states are indeed outgoing, even though they're really representing, and then again, this is going to be, sorry about that, it's Q bar, P2, 1, and this is going to be H bar, Q bar. So we can see right away there's going to be additional factors of H bar squared coming from the propagator. If we look first at electromagnetism, then we can simply write down maybe a rare example where there's no need to go to any fancy amplitude techniques, because we only have one diagram to write down. If we put in the on-shell conditions, then we can simplify the structure, and we get, I think I need to work this out explicitly. So we would get this expression for the amplitude, and you can see that there's this additional factor of H bar squared that neatly cancels the remaining H bar squared in front. So we had started with something that naively from the couplings was singular, but then localizing the integral properly actually made it of order H bar squared, but there's additional factors of 1 over H bar squared from the amplitude that overall give you something of order H bar to the 0, which is exactly what you expect for the classical limit. So we can now plug this in, and once we put in the values of m times u for the classical momenta, then in fact there's no more p dependence, and we can drop the angle brackets. And so let's say in the case of electromagnetism, we get this integral. And so, and U1 and U2 here are the classical 4 momenta of the two scattering particles. And what's left of the amplitude is, of course, the propagator, which is giving us the kernel of this integral. And then there's a numerator factor, which is just constant. It doesn't depend on Q. So this the u1.u2 is just a Lorentz factor, which is conventionally, I think, by the GR people called gamma, and has various different names in the literature by the Amplitudes people. We're going to, we can take the impact parameter to be orthogonal to the 4 velocities, and that's essentially choosing a frame of reference. And we now need to evaluate this integral. We don't actually have time to do this at the board, but I'll tell you there are many ways of doing it, but one convenient way of doing it is to choose a basis that's built up out of u1, u2, the b vector, and a vector that's built out of the that's built using a Levi-Civita tensor out of these 3 vectors, so u2 to the lambda, b to the rho. So you use that as a basis. You express q bar in terms of this basis in terms of coefficients, and then you integrate over those coefficients.
David,
and
raised hand.
Just well, let me finish this one. And the final integral you can do as a Fourier transform, and then you'll find an expression which you could also, of course, derive from classical E&M, that modulo a factor of 2, I'm not 100% sure about, has this form. And it's b mu over b squared. There's a minus sign here. So this is the result in classical E&M, and you can see at least the sketch of how it would emerge from this calculation. So yes, there was a question.
Yeah, sorry, I probably missed this part. Are you neglecting here the radiation effect, or will they show up at much later order?
So as I mentioned in the first lecture, the radiation actually shows up at higher order. We won't have time to discuss the radiation variable, but it doesn't show up at leading order. It doesn't show up at next to leading order. It shows up at next to leading order.
Oh, okay.
So it's being consistently included at this order because it's absent.
Okay.
Okay, so the one thing that we can do very simply here is to go back and see what would happen in gravity, or not exactly in general relativity, but in gravity with a dilaton, because that is what you get from doing the simple double copy of Yang-Mills, or in this case, it's equivalent to doing the simple double copy of QED. Then what's going to happen is you're going to retain the same propagator structure of the diagram, but the numerator is essentially going to get squared. And so up to higher order terms in H bar, you're going to get the square of that numerator. You're going to be replacing up to various factors, which I'm probably not going to get straight here. You're going to be replacing the E times, or E squared times Q1, Q2 by G Newton's constant times the product of the two masses. What's going to happen there is that P1.P2, of course, you're going to be, it's just going to turn into U1.U2. So here we're going to get a U1.U2 squared instead of U1.U2. The integral is then identical. So you can see an example concretely how the two calculations, which in classical field theory would look very, very different, are going to be very similar. And so in dilaton gravity, we would get minus 4I G M1 M2, and now instead of gamma, we would get gamma squared, and then divided by, the 2 pi's got absorbed into the definition of G. And then we would have the same B mu over B squared. It turns out in this particular case that actually subtracting the dilaton is not so hard. It just replaces the gamma squared with a gamma squared minus 1/2, but that lies outside the scope of this discussion. And this is in fact the same as the classical GR result, which has been known for a long time, but is considerably less trivial to derive. So I'm not going to have time to go through other observables, or for that matter, to discuss the next to leading order corrections. The only thing that I was anyway planning to do was to look at the cancellation of singular terms, but that's something that at least you've been warned about. What I do want to spend the remaining 40 or minutes or so, 40, 50 minutes, is another subject which is connected to the calculations that are needed for using this formalism. So much of the work that has been done in amplitudes is focused on massless scattering amplitudes. And here, as you can see, the kind of massives, in fact, several massive lines play a very intrinsic role. The kinds of amplitudes we're going to be often looking at involve at least one and more usually 2 distinct massive lines tracing through the diagram, and then some number of massless lines either being exchanged or perhaps being emitted as radiation. So I thought I would give a very brief introduction to massive spinors. I assume, as I think we already saw in the first lecture, most people have at least a passing familiarity with massless spinors, and I will more or less assume that, although I'll very quickly remind you of how that works. So we're going to look a little bit at massive spinors, kind of the most modern technology, and this is based on 2 papers, one by Arkani Hamed and Yutin Wang, and another younger Wang, and that's 1709, 04891. And also on a paper which I would describe as being more careful in its normalizations and especially in its signs, and that's Chung Wang. It's the same. It's Yutin it's the same Wang. That's the common between those two. Kim and Lee, which I'll sometimes refer to as CHKL. And that paper is 1812, 08752. So if you go back and read these, I recommend reading both. The first of them really gives a very good conceptual overview, but if you want to double check your signs and normalizations and things like that, it's better to refer to the second paper. So we know that we have, for example, the Park-Taylor amplitude, the endpoint amplitude with 2 negative helicity gluons, and the remaining gluons all of positive helicity. And now I'll switch to the usual convention where all momenta are taken to be outgoing. So we have a very, very simple form, which is given in terms of these objects, which are spinor products. So they're bilinears in the spinors that are associated with the external momenta. And this has been very important part of the whole spinor formalism has played a very important part in a lot of the developments. And so we'd like to understand how to extend that from massless particles, the gluons, of course, being massless, to massive particles. Whoops. I think I need to, something went wrong here. Is my screen back? Okay. So we introduce the 4-vector of Pauli matrices. And these have carry one Lorentz index, the upper index, and then they carry what are also Lorentz indices in disguise, but these are the Lorentz group thought of as SL2C. So instead of transforming on one as the vector representation, it's essentially conjugating by 2x2 complex matrices. And we can use these matrices to get a 2x2 matrix representation of momenta. So this is arbitrary momenta by contracting with these Pauli matrices. And these Pauli matrices, of course, are just the identity matrix along with the usual set of 3 Pauli matrices that we know and love from a long time ago. So if you work out the invariant tensor for SL2C, as you probably remember, is epsilon alpha beta, a 2x2 epsilon tensor. And if you work out in this language what the dot product looks like, then you'll find something. Actually, I should try to stick to a consistent convention here on the shape of the epsilons. Alpha beta, epsilon alpha dot, beta dot. So in particular, if we're looking at p squared, then we'll find that it's given in terms of the determinant of this 2x2 matrix. And for those of you who haven't seen this before, then you should show this by explicit computation rather than the formal manipulations that I've outlined. So in the massless case, p squared is of course 0, and that means that the matrix is singular and that it can be, therefore it has rank 1. It can be written as the outer product of a single set of 2x2 vectors, and these vectors are called, they're 2-dimensional complex vectors, and these are the spinors. So, and again, as a reminder, these are bosonic variables in spite of the fact that they transform under SL2C in the spin 1/2 representations. So lambda and lambda tilde. And every momentum has a pair of these corresponding, and these under little group transformations, so transformations that keep the momentum invariant, these things do transform non-trivially. These are essentially the phase or helicity weights, and they transform in opposite ways. So the amplitudes are going to be objects which are Lorentz invariant but have a non-trivial little group weight corresponding to the helicities of the external states. And the notation, of course, is just a shorthand for the dot products that are contracted. Oops, order. And there's a conjugate product as well, which is written with the bracket. So for massive momenta, p squared is no longer 0. So of course we need not just a single basis vector. We have to write it as a sum of 2 vectors. And there are many different ways of doing this, but the way that, whoops. Sorry, my computer has decided it doesn't recognize me. Is my screen still shared?
It is, yeah.
Okay. All right, so we now need not just one spinor and its conjugate are no longer sufficient, but we can still write the momentum as a sum over 2 of these. So we introduce the index I to represent the this pair of spinors. And the key point that Arkani Hamed and the 2 Wangs made is that you should think of this I as being an SU2 index corresponding to the little group for massive momenta. And you should treat them as doublets. So in the same way that the momentum itself would have a remaining vector degree of symmetry, these would have a spinorial degree of symmetry. And that way of thinking about it makes a lot of the symmetries more manifest. So there's an SU2 corresponding to the little group. Every external leg has its own little group that it transforms under, and the alpha index is inert here. So in the massless case, then the reflection of the anti-symmetry of the spinor products, we would have, for example, relations like this. This is just, or if I introduce it in terms of a slightly cleaner notation, this would correspond to the, so this vanishes, this would correspond to the p slash acting on lambda equals 0. So this is just the Weil equation, essentially in this language. Now, in the massive case, lambda and lambda tilde are not really so distinct. You can go back and forth between them because p no longer annihilates lambda tilde or lambda. It just converts it to a the other type of spinor, and that's just a reflection essentially of this language. It's just the Dirac equation written out. Now, so far I've been writing a lot of indices, and not everyone likes to spend their lives writing out indices, though I should note in parenthetically that probably the greatest theoretical physicist of the last third of the 20th century, Steven Weinberg, liked to write everything out in indices, and it, I think, worked out pretty well for him. So if you like to do that, more power to you. But it's convenient to have a slightly more streamlined notation. And we can kind of generalize the usual Bra and Ket notation as follows. We have I and lambda I alpha j. So again, we're using the label of the external leg as the label inside the bra or ket. This is going to be a ket upper index. So we can now write contractions in the usual kind of form. So in the sorry about that. The OneNote, hold on. OneNote seems to have crashed. Let's recover it. Okay. Sorry about that. So we can write contractions in the usual way. So instead of having all the indices, this would be here, it would be in the massless case, but it would work out very similarly. In the massive case, it's just essentially adding these capital Latin indices for the, so this we might write, for example, in this combined angle and bracket notation. And I like to use, although I don't know that I'll actually be making use of it here, notation with a free index corresponding to differentiating with respect to that, that momentum, or equivalently just having a set of sigma matrices. There's a B there. So we can, for example, write the massive momentum. If momentum 1 were massive, we can write it in the usual kind of Gordon identity form. There are two slightly, two equivalent forms. And this is something where you have to be a little bit careful, because these indices, these SU2 Latin indices are again contracted with the SU2 invariant tensor epsilon ij. This has numerically the same form as the epsilon alpha beta and epsilon alpha dot beta dot, but it's logically a distinct tensor. That's what's contracted, and of course, because of the anti-symmetry, then there are relative minus signs. So there are various useful identities you can write down. So when you have different spinors, of course, they don't necessarily vanish anymore. They would only vanish in the massless limit. So the spinor product of two lambda tensors would be something proportional to the epsilon tensor. Likewise, for the bracket, the lambda tilde tensors are bracket product. And one can write down a whole list of identities like that. If you now contract some of these, then again, you see things that from a usual massless spinor point of view look a little bit strange until you realize that there are actually different objects that are being contracted here. This is really an A sub 1 with an A sub 2, for example, the second of the two. And again, the same conversion equation, the Dirac equation that we wrote down earlier, has a more streamlined form here. It converts angle and bracket spinors to each other. So the last kind of preparatory thing we need to think about is how we're going to express the amplitudes. So in the massless case, we always have two states. And in the scalar case, I'm thinking of complex scalars. So you can use the same labeling, and you can always label them plus or minus corresponding to the positive and negative helicity, even if the helicity is 1/2 or 3/2 or 2 or 1. One of them is positive and the other is negative. So for example, for gravitons, we would have helicities +2 and -2, but we can label them just as plus and minus. Now, in the massive case, it's we have spin S, of course, has 2s plus 1 distinct states. So a massive vector would have 3 states. And I'm sure all of you in your undergraduate quantum mechanics courses were taught to write out these states in terms of the total spin and spin along some angular momentum along some axis, usually the z-axis. And for the purposes of the massive spinorology, you should unlearn all of this, because it is not a good way to think of relativistic amplitudes. It breaks Lorentz invariance, and it's ugly, it hides structure. Instead, and this is the other kind of insight of AH squared, is to think of the spin S particles as corresponding to symmetric tensors with appropriate number of indices of SU2. So in general, if we had a 2s index tensor in n components, then we would have had n plus 2s minus 1 factorial divided by n minus 1 factorial 2s factorial distinct elements. And here, of course, we have 2 different components because it's SU2. And so for n equals 2, this gives us exactly 2s plus 1, which is what we want. And you can also see, for example, if you take the tensor product of 2 spin 1/2 representations, that you get the symmetric product, which is going to be spin 1. And the antisymmetric product is necessarily going to be proportional to epsilon AB, and that's, of course, going to be the scalar, and that corresponds exactly to the way things work in SU2. So that says that we have the first representation for our amplitude, which is to write out, as usually, the helicity labels for the massless particles and the symmetrized sets of these SU2 little group indices for the massive higher spin particles. So for example, if we had a 2 spin 2 massive particles in numbers 2 and 3, and 2 massless particles, I haven't really specified what their spins are. You can imagine them being spin 1, for example, massless spin 1, then we might look at a typical amplitude or result, explicit result for this kind of an object. So that's one representation. And because in this case, unlike the massless case, we can trade all the appearances of lambda tilde using K for appearances of lambda, then we can always make sure that every external spinor is represented by a lambda, and we can factor them all out. And then we could write our amplitude in terms, for example, for some massive state, we would have symmetrized indices. So it's all the same lambda j, but different, principal different Lorentz SL2C and little group indices, symmetrized in all of them. So we have, let's say, 2s here and 2s. And then we can write a second representation of the amplitude in terms of a set of symmetrized little group indices. And both of these representations are convenient at different stages of a calculation. So the last notational aspect is, again, has to do with the indices that would otherwise clutter the page. So you might end up writing expressions, for example, related to that amplitude that I mentioned above with two massive two-spin particles. You could imagine writing out some expression of this sort. So we might have 2 to the I3, 3J1. And unlike the case of massless particles where there's a definite weight, and so there's a definite net number of brackets and spinors, and terms have to be homogeneous, here it's the behavior under the little group indices, the capital Latin indices, that matters. So you can have terms that look odd from a massless intuition point of view, that they have kind of strange mixtures of angle and brackets. So here we would have, for example, some term, an expression of this sort that might show up. And you can see that, and of course, it's always implicitly symmetrized in both the I's and the capital J's. So there's a lot of indices strewn out, and it's also unnecessary because if we had a compact notation, we know how to recover this explicit form just by writing out the fully symmetrized form. So we can actually drop the indices. And in the literature, that's done by bolding the labels that are associated with the massive external states. It's a little bit hard to do that here, so instead I'll underline them. And the power counting corresponds to the original power counting, and I think you can see that the second expression, which has exactly the same information content as the first, is a lot less cluttered. So in the remaining kind of 15 minutes or so, I want to look at a set of simple amplitudes. The philosophy, again, is very similar to that in the massless case. You can write down the most general form of the 3-point amplitudes, and then you can build up all higher point amplitudes out of these basic 3-point amplitudes. The difference is that our techniques are not as developed, and you don't have the same kinds of recursions. You have to rely on explicit factorization arguments at the moment, although I think there's some hope that that will again get streamlined. So let's look at kind of the simplest case that introduces a massive vector. So let me call it the decay coupling. So this is something where we have two massless particles and one massive particle. So unlike the fully massless case, here we don't need to worry about complex momenta because this is actually a process that could happen physically, although of course one can again, and it may be convenient for some purposes to go to complex momenta. In fact, to understand the analytic structure it is. So let's assume that 1 and 2 are massless here, and there's some spin s massive particle, which therefore has the Lorentz indices, the SL2C indices, 1 through 2s. So to write out the amplitude, it'll be convenient to start with the second form, or at least think conceptually in terms of the second form, where we have symmetrized SL2C indices. And we have two independent, we could use a basis for them. We need two it's a two-dimensional space, so we need two independent vectors, and lambda 1 and lambda 2 form a basis for those vectors. And once we've done that, then we can recontract with all the lambdas, the lambda i's corresponding to the third leg, the massive leg that we've pulled out. And also in writing out this expression, I'm going to drop any couplings or any Lie algebra factors that might be associated with the masses, or for that matter, the massive legs. And once we've done that contraction, we can write the general form of the amplitude as some powers of the mass, which we'll need in order to get the dimensions straight. And then using this bolded, or here underlined, notation, we have some powers of the different spinor products. So there's 1 contracted with 3 and 2 contracted with 3, and then we can contract the remaining. So the 3-point amplitude should have dimension -1. That gives us one equation. And there are the phase or helicity or spinor weights associated with the two massless legs. That gives us, for leg 1, it's going to be eta 3 minus eta 1, should be equal to twice the helicity of leg 1. Again, the helicity, of course, is given in units of 1/2 rather than integer units. And likewise, there's a similar constraint for leg 2. So eta 3 minus eta 2 is given by the helicity of leg 2. And finally, the tensor structure, we know that we have to have the right number of tensor indices. So there's a constraint on the sum of eta 1 and eta 2. And that has to be equal to 2s. So we have 4 linear equations in 4 unknowns. So there's a unique answer. And we can solve that to find that we have, this is s plus h2 minus h1. And this one is 2, 3. Of course, the corresponding form plus h1 minus, let's actually clear that up a little bit, minus h2. And finally, there's a bracket product s with the sum of the two. And denominator, we have an appropriate power of the mass to get the dimensions straight. Oops. Able to see the entire screen now. So that's the first simplest amplitude we can look at. And the one thing we can see right away, but I'll leave that as an exercise, is obtain Yang's theorem, which says that a massive spin 1 particle cannot decay into a pair of photons. And again, that's here, it's just write down the structure, write down the general result. And this theorem, which was a much more non-trivial result when it was first obtained, I guess, in the 1960s, just plops right out. So let me actually go on to the, what would have been the third case, but let me skip over the unequal mass case. So let's look at the equal mass case with 2 massive vectors. So here we'll have one massless and 2 massive states. And again, in the unequal mass case, one could imagine, for example, using, let's say if we have leg 1, leg 2 and 3 are massive. These indices I'll use alpha and beta. So if the masses hadn't been the same, we could have imagined using basis vectors, for example, K2 acting on bracket 1 and ket 1 as a basis in the same way that we used 1 and 2 as the basis. But if the masses are the same, then we can see that this is just going to be equal to 2k1 dot k2, and that thing we can just write out in terms of the masses. It's of course k3 squared minus m2 squared, and so by assumption of the equal masses, it's 0. So these are in fact no longer linearly independent, that is, they're collinear. So we only really have one independent spinor, but there is information in the constant of proportionality, which is called x in the literature, so I'll keep that as well. And that x is defined as follows. It's a dimensionless ratio. And we can also write it the other way around by converting from the angle ket to the bracket ket. So notice that under the little group associated with the massless leg, x actually carries some little group weight or phase weight. So it will play a role, that will play a role in constructing the examples, in constructing the amplitude. Now, there's no manifestly local expression for x, but we can write x if we introduce some reference spinor, then we can write it not in this awkward way with indices still floating around, but we can write it in a computationally more convenient form that involves, it seems to involve the spurious pole, but that in fact is fictitious. So if we now want to express the amplitude, we still need two independent objects, but the objects that we now can use are we can still use one of these two, lambda 1. And the other object, the only other object we have that's available is the invariant tensor epsilon. So we can now try to build out the amplitude using these two objects. So we're going to have some power of this x variable, and then we're going to build the tensor. We have an object with indices, and let me just call the number of those 2 and 1 because it has one index and the epsilon tensor correspondingly has 2. And let me call the number of epsilon tensors eta 2. So this will have the appropriate number of symmetrized indices in the alphas and in the betas corresponding to the spins of the second and third legs. Now, the most typical situation, of course, will be those spins being equal, but they don't have to be. So from the weight, the phase weight or the little group weight of the massless leg, we have one equation, which I can write in the following form. So 2nx minus 2n1 is again given by twice the helicity of particle 1. And from the number of indices, we have twice times n1 plus twice n2 is given by 2s2 plus 2s3, just counting the indices. And we do have to be a little bit careful because we're putting in an anti-symmetric object here, and we want the indices to be symmetrized, so we have to avoid trying to anti-symmetrize some symmetrized indices. And that says that n2 has to be less than the minimum of 2s2 and 2s3. So in this case, we actually have two equations, but there are three unknowns. So we don't have enough equations to fix everything. And that tells us that, in fact, we're going to have a sum over different possible tensor structures and hence different possible couplings. So the general form of the amplitude will have this sum over eta 2 running up to twice the minimum of S2 and S3. And once we know eta 2, then we can simply solve for eta 1 and then also for eta x, which is just given by h1 minus n1. And I leave it as an exercise to write it out in terms of write out all these tensors in terms of the explicit appearance of the bolded angle and bracket kets associated with the third and second legs. So of these, there's a certain sense in which some of these couplings, or one of these couplings, is actually naturally minimal. And if we focus on the equal spin case, then for the positive and negative helicities of the external massless particle, we actually get a much simpler form in spite of the somewhat formidable expressions that I've just written down. So we have a 2s power divided by an appropriate power. Of course, there's a single mass because by assumption, the mass is the same for both legs 2 and 3. And correspondingly, minus and again, the two spins would have a 1 over x, and here there's a bolded bracket of the two massive legs with the same normalization in terms of the mass. So, it might have been a nice exercise to go through the construction of the at least the simplest 4-point amplitude, but I think that would cause me to run a little bit further over than I'd expected. If people ask the question and the rest of the audience has tolerance, I can at least sketch that out. But let me stop here.